Welcome back. In this video, I'm going to solve exercises 9 to 11 of chapter 4. Exercise 9. We have an infinite dimensional normed space E, which either has a separable dual or it is reflexive. We have to show that there exists a sequence in the unit sphere that converges weakly to 0. So this is a very general result, showing that weak convergence and strong convergence are not equivalent. Because if we find a sequence in the unit sphere that converges weakly to 0, the sequence in the unit sphere has norm 1, so it cannot converge strongly to 0. Okay. So suppose first that E star is separable. Then, as we know from the lectures, the unit ball of E, the closed unit ball of E, is metrizable in the weak topology. Okay. And we know also from the lectures that since E is infinite dimensional, the weak closure of the unit sphere is the closed unit ball. Okay. So what do we have now? We have that BE is metrizable and is the weak closure of the unit sphere. Therefore, by proposition 0.3, every element in the closure in BE is the weak limit of a sequence in SE. Okay. So in particular, it's true for 0. Since 0 is in BE, 0 is the weak limit of a sequence in SE. Okay, so there is a sequence in the unit sphere that converges weakly to 0. Now, the second alternative, what happens if E is reflexive? This is a little bit harder. So, since E is infinite dimensional, as you know from chapter 0, there is a countable linearly independent set, E1, E2, an infinite countable linearly independent set, E1, E2, and so on. So we consider two subspaces. The first one is not closed necessarily because it's just the linear span of this E1, E2. So it's the smallest subspace that contains E1, E2. But it's not necessarily closed, so we take its closure, okay? Because we need to work in a reflexive space. Okay, so then of course M is infinite dimensional because M0 is infinite dimensional. It's reflexive. Why? Because it's closed. M is closed because it's a closure in a reflexive space. Okay, so a closed subspace of a reflexive space is reflexive itself, and you can prove that it's separable essentially because M0 is separable. Okay, so if you take the set of linear combinations of E1, E2, etc. with rational coefficients, then this set is countable and it's dense in M. Okay, so we encountered this idea before. Okay. And therefore, I can apply the first case to M actually. So we know from the course that if M is reflexive and separable, then its dual is also reflexive and separable. Okay. So we need the reflexivity assumption because if M is separable in general, it doesn't mean that M star is separable. Okay. We already proved that in the exercises. So we can apply now this to the first part. So there exists a sequence in the unit sphere of M converging weakly to 0. Okay. Here we cannot say that there exists a sequence in SM converging to X for any X in the unit ball of E because if X is in the unit ball of E, it doesn't mean that it's in the unit ball of M. Okay, this is okay. So, and that's it. So this concludes exercise 9. And in the next chapter, we'll give more examples of weakly convergent sequences which are not strongly convergent. Okay, so exercise 10. We consider the space of continuous functions from 0, 1 to R, and we equip it with the supremum norm or the maximum norm or the infinity norm that you need to know by heart by now. And there are several questions actually, and we asked part of these questions in previous exams actually. So one of the targets of the exercise is to prove that the space C01 is not reflexive. Okay, I mentioned this fact before, but I didn't give the proof. Okay, Proof is not difficult, actually, and it illustrates the basic concepts of this chapter. So the first question, we consider the Dirac operator, delta t, which is an evaluation map, basically. So given a number t between 0 and 1, delta sub t associates to each element u, to each continuous function from 0, 1, its value at t. So it's just a real number. Okay? So I have to show that for each t, delta t is in the dual, and we have to compute the norm. So this is easy. Second, we have to use that if un converges weakly in E, then un converges pointwise. So weak convergence in this space implies weak pointwise convergence. Third question, we have to show that the converse is not true by considering an example. Fourth question, study the pointwise convergence of the sequence, Vn, and then we have to deduce that C01 is not reflexive, and then deduce that L infinity is also not reflexive, the fact that I mentioned. Okay, so let us start by question 1. So the operator delta t is of course linear because delta t of u plus v, as you may check, is delta t of u plus delta t of v, and if you multiply by a constant, you should be able to check that. And delta t of u is just u of t, and so u of t is less than the maximum of u. So delta t is bounded, and it has norm 1, less than 1. But actually, the norm is exactly 1, because if you consider the constant function equal to 1, then this function is in the unit sphere, and delta t at this function is just v of t, which is constant, so it's 1. Okay, so therefore, the norm of delta t, which is by definition the supremum of absolute value of delta t on the unit sphere, the supremum is bigger than any value. So in particular, the supremum is bigger or equal than delta t of v, because v is in the unit sphere, and this is 1. So actually, we have a double inequality and therefore equality. Second question. Okay, if un converges weakly to u, then we know from the course that f of un converges to f of u in R for every f in the dual of E. Okay? So in particular, delta t of un converges to delta t of u for every t, and this means that un of t converges to u of t, of course, in R, because un of t and u of t are real numbers. So this convergence in the usual convergence in R. So here, un and u are functions, are elements of the normed space, but u of t and un of t are numbers. Okay. So this is just the definition of pointwise convergence, convergence simple. Now, if you go back to the sequence, if you study the variation of this sequence, as you know from first year or even from high school, take the derivative and you see where the derivative is positive, where it's negative, so it's increasing, decreasing. It has a maximum at 1 over n plus 1, and when you compute the maximum, you'll find this expression. Should be able to do that. And now what happens as n tends to infinity? The term here actually tends to 1 over e, as you know, and this tends to infinity actually. So the norm infinity of un tends to infinity. So un is not bounded, and therefore cannot converge weakly, because a weakly convergent sequence is necessarily bounded. Now, for the sequence Vn is just has a triangle shape, so it starts from 1 and decreases linearly to 0, and then becomes 0. So we should easily draw the graph of this function. Now, so consider now an element t between 0 and 1. Okay, so let me go back to the this is the shape. So it's an equation of a line. So it's when t equals 0, it's just 1, and when t equals 1 over n, it's 0, and then it remains 0. Okay, we have to study the pointwise convergence of this sequence. Okay, so if you draw the graph of this function, you will convince yourself that Vn converges to 1 if t equals 0, and converges to 0 if t is bigger than 0. Okay, so it converges to a discontinuous function limit. Okay. So if t equals 0, Vn of 0 equals 1, and so Vn of 0 converges to 1. If t is positive, we choose an integer n0 bigger than 1 over t. So now if n is at least n0, then t is bigger than 1 over n0, so it's bigger than 1 over n. And by definition of Vn of t is 0. So it converges to 0. So therefore, Vn of t converges to the discontinuous function, which is 1 at 0 and 0 elsewhere. Okay. Now, we have to deduce from this that C01 is not reflexive. So suppose that it's reflexive. If we consider this sequence, Vn, the norm of Vn is 1, because the maximum is 1. It's achieved at 0. And so Vn is bounded. So if C01 was reflexive, then Vn, which is bounded, should possess a weakly convergent subsequence, Vnk, that converges to some limit, W. So the limit must be in the space, so it's necessarily continuous. But by B, we know that Vnk converges pointwise to W, because weak convergence in C01 implies pointwise convergence. Okay, so yeah, this is Vnk, not Unk. Please correct that. So Vnk converges pointwise to V. And so by uniqueness of limits, we should have W is equal to V. Okay. But this is a contradiction because W is continuous, but V is not continuous. Therefore, our assumption was not true. So C01 is not reflexive. Now, why L infinity is not reflexive? Because why? Because C01 actually is a complete space for this norm. So it's closed in L infinity. Okay? The norm in L infinity and the norm in C are the same. So C01 actually is closed in L infinity because it's complete. If L infinity was reflexive, then C01 as a closed subspace would have been reflexive. So L infinity is bigger than C01. Okay, so if the small space is not reflexive, the bigger space is not reflexive. So this concludes exercise 10. Exercise, yeah, so let me end by a remark actually, how to characterize weak convergence in C01. Un converges weakly to U in C01 if and only if Un converges pointwise to U and Un is bounded. Okay, so 1 implies 2 is easy. You should be able to do that because we proved in B that weak convergence implies pointwise convergence, and we know that weak convergence implies boundedness. So of course 1 implies 2. 2 implies 1 is more interesting, but more difficult actually. But let me give you the idea. Suppose that Un converges pointwise to U and it's bounded. Okay, we have to prove that Un converges weakly to U. How do we prove that? We prove that f of Un converges to f of U for every f in the dual of C01. Now, as I mentioned in chapter 0, I mentioned the Reed's representation theorem, which is a difficult theorem outside your program, but you should know about it. So we have a representation of any element in the dual. So for every f in the dual of C01, f of V can be written as the integral over Lebesgue integral over 0,1 of V, and we integrate against a Borel measure mu, which is actually what we call a signed measure. So it could be positive or negative, actually. Okay, and the same theorems that you studied last year in the Lebesgue theory actually apply for this more general concept of measure, what we call signed measure. So since Un is bounded and converges pointwise to U, then the Lebesgue dominated convergence theorem for this measure so implies that the integral of Un converges to the integral of U. Okay. And this means that f of un converges to f of u. Okay. So this is just for your general knowledge, but the Reed's representation theorem is not part of your program. Okay, so last exercise, 11, is actually optional because it's a little bit lengthy. So, but I will solve it anyway. So this is actually, I mentioned this in the lectures. I gave 4 characterizations of uniform convexity. The first one was the definition: for every epsilon there is delta, such that for any 2 elements in the unit sphere, if their distance is bigger than epsilon, then etc. And I told you that we can replace the condition xy in the unit sphere by xy in the unit ball. Okay, so if you think of uniform convexity as being the uniform roundness of the unit sphere, the second condition tells you that the ball is also uniformly round. And you have a characterization of uniform convexity by sequences. So if the middle point of 2 points in the circle tends to 1, or tends to the unit sphere, then necessarily these 2 sequences are asymptotic. And here, of course, you can take the sequence in either in the unit sphere or in the unit ball. Okay. So you don't need to follow all the details or to understand all the details, because it's a little bit lengthy and even took me some time to figure it out. But you should know the result. So the proof is not circular. The only proof I found is that prove that 1 is equivalent to 3. 2 is equivalent to 4, but similar. So the equivalence between 1 and 3 is the same as the equivalence between 2 and 4. So if you understand the first equivalence, then the second one will follow. Then the hardest step is to prove that 4 implies 3 actually, and 3 implies. So 4 implies 3 is easy, but is trivial. But 3 implies 4 is the most difficult step. Okay, so 1 implies 3. So take 2 sequences xn and yn in the unit sphere, whose middle point converges to the unit sphere, let us say, put it in this way. And we reason by contradiction. Suppose that xn minus yn does not converge to 0. Okay? So we have to negate the condition for every epsilon, etc. If you negate this, you will construct a sequence x and k and the sequence y and k whose distance is bigger than epsilon. Okay, I think we did something similar in the class. So just write the negation of the convergence to 0 by going, okay, so, and then you'll convince yourself that there are 2 sequence, so 2 subsequence actually, x and k and y and k. Now, it's a practical mathematical tradition that in order to avoid subscripts, we may still denote the subsequence by the same symbol in order to not to have many subscripts. So we may assume that xn minus yn norm is bigger than epsilon for some epsilon. Now, since E is uniformly convex, the middle point of xn yn should be inside. So it should be the norm of the middle point should be less than 1 minus delta, where delta is the modulus of uniform continuity corresponding to this epsilon. And so if we let n tend to infinity, this norm tends to 1. So we get 1 is less or equal than 1 minus delta, and this is the contradiction. So you should understand this simple reasoning actually. It's not terribly difficult. So we can ask such questions in the exam. Okay, 3 implies 1. We reason by contradiction, so we negate the condition of uniform convexity. So there exists epsilon for every delta, there exists xy, etc. And now we cannot change the epsilon, but we have a choice in choosing delta. So we take first delta equal 1, then 1/2, then 1/3, and so on. And at each step, I get 2 elements in the unit sphere whose distance is bigger than epsilon, and the norm of the midpoint is bigger than 1 minus 1/n. So I have 2 sequences now, xn and yn, in the unit sphere. whose distance is bigger than epsilon, and the midpoint, the norm of the midpoint, is bigger than 1 minus 1 over n. Now, since xn and yn are in the unit sphere, then the norm of xn is 1 and the norm of yn is 1. So by the triangle inequality, the midpoint has norm at most 1. So what do we have? So the norm of the midpoint is between 1 minus 1 over n and 1. So by the sandwich theorem, the norm of the midpoint tends to 1, and therefore by our assumption, we should have xn minus yn tends to 0, but this contradicts this inequality. Therefore, we have the uniform convexity condition. Now, if you understood this equivalence, then of course, so 2 implies 4 is similar to 1 implies 3, and 4 implies 1 is similar to 3 implies 1. Just replace SE by BE. So same thing. 4 implies 3 is trivial, as you said, because as the unit sphere is a part of the unit ball. And now the most complicated proof is 3 implies 4. So consider two sequences xn and yn in BE, whose midpoint converges to the unit sphere. So norm of xn plus yn over 2 tends to 1, or equivalently, the norm of xn plus yn converges to 2. Okay, since xn is bounded, the norm of xn is a bounded sequence of real numbers. We know from calculus that it has a subsequence that converges to some a. So may still denote the sequence by the same symbol to avoid subscripts. Okay, so the norm of xn converges in R to, of course, to a non-negative number. Now we'll prove that a cannot be 0. Okay, so let us write the triangle inequality in this way. The norm of xn plus yn is less than the norm of xn plus the norm of yn. So when I raise to the power 2, I get this is less than this, and then I take the minus. So this minus square here is bigger than this minus square here, and then I add twice the norm of xn square plus twice the norm of yn square. So now, if you look at this left-hand side, what can we say? The xn and yn are in the unit ball. So the norm of xn is less or equal than 1, and the norm of yn is less or equal than 1. Therefore, this guy is less or equal than 4. So this term on the left here is less or equal than 4 minus xn plus yn squared. And now if you look at the right-hand side, you do the usual algebra. This is just 2a squared plus 2b squared minus a plus b squared. Not the same a, actually. So this is just norm of xn minus norm of yn squared. Okay? Just expand this simple algebra. So what do we have now? Therefore, we have 4 minus norm of xn plus yn squared is bigger or equal than, or the other way around, xn, the norm of xn minus the norm of yn squared is less or equal than 4 minus this guy. Now, since xn plus yn in norm tends to 2, this guy tends to 0. So by the sandwich theorem, this guy, which is non-negative, tends to 0 as well. So, and since xn in norm converges to a, it means that the norm of yn also converges to a, which is non-negative. Now, suppose that a is 0. If a is 0 and we have norm of yn tends to 0 and norm of xn tends to 0, this means that xn converges strongly to 0 and yn converges strongly to 0, and therefore the middle point should also converge to 0. But actually, the middle point converges to 1. So this is a contradiction, and therefore a is strictly positive. Now we rewrite the inequality, the previous inequality. 4 minus xn plus yn squared is bigger than this guy, and this is bigger than the difference in. Now, norm of xn tends to a, norm of yn tends to a, so this guy tends to 0. And this guy converges to 4, therefore this, the difference here converges to 0. So this term converges to 0, this term converges to 0. Therefore, by the sandwich theorem, the middle term here converges to 0. Okay. Now, if you look at the middle term, this term converges to 2a squared, so 4a squared. Therefore, xn plus yn, the norm of xn plus yn squared converges to 4a squared. Or equivalently, the norm of xn plus yn converges to 2a, which is strictly positive. But xn plus yn norm converges to 2, and therefore 2a equal 2, therefore a equal 1. Okay, so the norm of xn converges to 1, and the norm of yn converges to 1. Therefore, xn and yn cannot be 0 so they are different from 0 from a certain rank. So therefore, we can divide by the norm of xn and the norm of yn. So, but now xn over its norm and yn over its norm are now sequences in SE. So we can apply what we said, the condition. Now, since the norm of xn over its norm is 1, so by the triangle inequality, xn over its norm plus yn over its norm is less or equal than 2, 1 plus 1. And if we use the second form of the triangle inequality, so if you consider xn over its norm plus yn over its norm, and you add and subtract yn over the norm of xn, by the second form of the triangle inequality, this is bigger or equal than the norm of this first two terms minus the norm of these two terms. So we can put the minus outside, so minus. Now, the norm of these two terms, we have norm of xn in factors. So this is just the norm of xn plus yn over norm of xn. And if you look at these two terms and take the norm, you'll get norm of yn in common. And then you'll get 1 over norm of xn minus 1 over norm of yn. But you have to take the absolute value. So this is just, so the second term is, the norm of the second term is equal to this. Okay, now this converges to 2, this converges to 1, so this is 2. And since norm of xn and norm of yn converge to the same limit, which is 1, then the difference tends to 0 because yn is bounded. So this the term on the right-hand side converges to 2. And this guy is less or equal than 2. So the norm of this guy is, by the sandwich theorem, tends to 2. And by our assumption, it means that the distance between these two sequences on the unit sphere converge to 0. Okay, one more step. We use the same trick. So we add and subtract yn over the norm of xn. And we use the second form of the triangle inequality. So the norm of this difference minus the norm of this difference. So we get norm of xn minus yn over norm of xn minus absolute value of this difference times norm of yn. And therefore, if we add this term here, we get that, so we add this guy, so we get norm of xn minus yn over norm of xn is less than this plus. Now this tends to 0, this tends to 0, therefore norm of xn minus norm of yn tends to 0, but since xn converges to 1, we see that the numerator, so if you multiply by norm of xn, which is bounded, then we get norm of xn minus yn tends to 0, and this finishes the proof. So it's a little bit lengthy and complicated, but that's it. So this concludes this third part of the exercises. Thank you for your attention, and see you next time.